Perform normalization of the wave function psi of x equal x squared over the interval 0 to k. Welcome to LIB Academy, and we'll be looking at normalization of the wave function with practical problems. The general Schrodinger equation, which is the fundamental equation in quantum mechanics, is a second order partial derivative differential equation. So solution of this gives us something called wave function, which we usually use psi to represent those functions. And it turns out that solution from this gives us a lot of wave functions in terms of psi. Like any other partial derivative second order differential equation, solution from it will give you a lot of wave functions. But Max Born said that the absolute square of the wave function should have something to do with the probability of us finding a particle in the system. And if we integrate from negative infinity to to positive infinity, which is the entire space, we must find the particle there. And the probability of us finding the particle there should be equal to 100%, which is 1. It shouldn't be 0.2, which is 20%, or minus 0.2, which is minus 0.2%. Because it turns out to be difficult for us to define probability in terms of minus values. It's kind of not making sense. So Max Born said that if we take the absolute square of the wave function and its conjugate, or the wave function simply integrate from negative infinity to positive infinity, or the entire space, the probability of us finding a particle within that space should be equal to 1, which is 100%. But because solution from the Schrodinger equation gives so many wave functions, some of the wave functions turns out not to give us a positive result to interpret. Can get negative probability. So to solve this problem, the wave function that should actually describe a row system should be positive, lead us to normalization of the wave function. Normalization of the wave function. And normalization of the wave function simply means that the wave function that is not normalized, we should add a certain constant to it and take its absolute square and integrate. Then after integrating, we should get 100% probability of finding the particle within the system. That is if the particle exists. And this n here, when we solve it, becomes a normalization constant. So in this case, we are looking for a constant that when we multiply by the wave function, will give us 100% probability of finding a particle when we integrate throughout the entire space. So in this case, this wave function, we can be able to use it to predict physical systems. And multiplying the wave function that we get from solution of the Schrodinger equation does not change anything, because it turns out that from second order partial derivative equation, if you solve it, you get a solution, and that same solution you multiply it by a constant, it doesn't change anything. So that is what you need to know. So we are given a wave function that is not normalized, and we have to normalize this wave function. So the first thing we need to do, since the wave function is not normalized, we have to multiply the wave function by the normalization constant. We can choose any letter since it was not indicated in the question. So let's say our normalization constant n, then x squared. Now we are going to solve for this here. And we've been given an interval from 0 to k. So to find to normalize this problem, we take integral from 0 to k of the wave function squared, or squared in terms of x, so dx. And the wave function now is nx squared. So integral from 0 to k nx squared all squared dx. It should be equal to 1. We are normalizing it. When it's normalized, when we evaluate this whole thing, it should give us 1. So now let's simplify this whole term right here to solve for the normalization constant. we are going to integrate. So let's do a quick revision on integration. If I am to integrate x to the power n, it should be equal to x the power increased by 1. And after that, I'll divide the whole thing by the power, which is n plus 1. So integrating x to the power 3 equal to x to the power 3 plus 1, 4, divided by 4, plus our integration constant. If I'm giving intervals from 0 to 1 to integrate the function x squared dx, now I'll first integrate this. So x to the power 2 plus 1, 3, divided by 3. So now evaluate it from 0 to 1. So doing so would be, first, wherever I see x, I put 1 there. So 1 to the power 3 over 3, then minus, wherever I see x, I put 0 there. So 0 to the power 3 over 3. So simplifying this whole thing to give me 1 on 3. So that is how integration is done. So let's proceed. So now we are integrating this. So from 0 to k, squaring, expanding this whole term. So n to the power 2 is n squared. Then x to the power 2 gives us x to the power 4. I just multiply this by that. So x to the power 4, the x equal 1. Now, since n is a constant, let's bring it out. So n squared integral from 0 to k, x to the power 4, the x equal 1. Now, let's integrate this term. So 4, the power increased by 1. So x to the power 4 plus 1, 5, all divided by 5. Don't forget, we have a constant here, n squared, multiplying. So now the interval from 0 to k, indicate them here. So this should be equal to our n squared is here, multiplying. We first put in our upper limit. Wherever we see x, we put k there. So k to the power 5, all on 5, minus, wherever we see x, we put 0 there, the lower limit. So x 0 to the power 5, all on 5, or multiplying. So now this will give us n squared multiplied by k to the power 5, all on 5. Any number 0 to the power 0 is the same as 0, and 0 over 5 will make this whole term goes 0. So just as this, it should be equal to 1. So now we have n to the power 2 multiplying k to the power 5, all over 5, equal 1. So let's multiply both sides of the equation by 5. So this 5 will take care of that 5. So we are going to get n squared k to the power 5 equal 1 by 5, which is 5. We are looking for n squared. So let's divide both sides of the equation by k to the power 5. So doing so, k to the power 5, k to the power 5, this will take care of that. So we're left with n squared equal 5 over k to the power 5. So let's take square root of both sides. This will cancel that. So our normalization constant is now equal to 5 over k to the power 5. So this is our normalization constant, that if we multiply it by the wave function here, the probability density should be equal to 1. So now let's write our normalized wave function. Our normalized wave function, psi of x, is now psi of x equal n x squared, but we now know n, which is our normalization constant, to be square root of 5 over k to the power 5. So square root of 5. We have 5 over k to the power 5 or root, then the wave function, which is x squared, then x squared. So now this wave function is now normalized. So this is a normalized wave function. With the intervals given, if you want to prove that, you can take integral from 0 to k of this whole term here squared to c. You will get a value to be 1. That is how to prove that a wave function is normalized. Normalize the given wave function for a particle in a box, given that psi of x equal sine 2 pi x. So this wave function psi of x is not normalized, and we want to normalize it. So if the wave function is normalized, it should be in a form, let's say our normalization constant a should be multiplying the wave function psi 2 pi x, psi 2 pi x. So we first have to solve for the normalization constant. But we have not been given any limit. But we know that we are dealing with a particle in a box. For a particle in a box, there is zero chance outside of finding the particle. Outside the box, there's zero chance of finding it there. But inside the box, let's say there is one chance of finding the particle there. The particle has nowhere to go outside the box. It is in the box. So zero chance outside and one chance inside. So that should be our integration limit. So 0 to 1, we are integrating psi of x squared. So psi of x absolute squared. And this is the same as that over here. So from 0 to integral from 0 to 1 of a sine 2 pi x all squared dx should be equal to 1. So now let's simplify the expression. So a squared, we are going to get a squared integral from 0 to 1. Then sine squared, sine 2 pi x multiplied by, to the power 2 is going to give us sine squared 2 pi x dx equal 1. Since a is a constant, our normalization constant, we can bring it out. A squared integral from 0 to 1 sine squared 2 pi x dx equal 1. Now what do we do next? We want to integrate sine squared 2 pi x. To do so, we are going to use the reduced angle formula in trig. We know that sine squared theta equal 1 minus cos 2 theta over 2. So sine squared can also be written as 1 minus cos 2 theta. In this case, this whole thing is our theta. We are multiplying this whole thing by 2. So it's going to give us 2 multiplied by 2 pi x, which is 4 pi x. Cos 4 pi x, then all divided by 2 dx should give us 1. Now, this over 2 here is the same as, it's more like this term multiplying by half, then simplified to be over 2. So we can take half outside, factoring these 2 out. So we can get it to be a to the power 2 multiplied by half from 0 to 1. 1 minus cos 4 pi x, the x equal 1. We just factored 2 out. So now we can simplify this as a squared over 2 integral from 0 to 1 minus cos 4 pi x dx equal 1. Now we want to integrate this. If we integrate a constant, let's say integrating 1 is going to give you x, 1x. 2 is going to give you 2x. 5 is going to give you 5x. That is if you are integrating. So integrating 1 gives us x minus. So integrating cos 4 pi x, what do we get? If you are integrating cos x dx, what you get is sine x. Integrating cos kx equal 1 over k, the term over here, 1 over k sine kx. Integrating sine kx equal 1 over k here minus 1 over k here multiplied by negative cos kx. So the whole thing becomes minus 1 over k cos kx. So now let's apply this here. So here, the variable that we are working with is x. So anything here that is not part of that becomes our k, right? So 1 over 4 pi. So 1 over 4 pi. And then if we integrate cos, what do we get? We get sine. So sine of everything here. Sine 4 pi x. Then we bring in our limit from 0 to 1 to give us 1. There's no need to include the integration constant here. So at the end of the day, it will be of no use to cancel out. Now let's continue. So let's apply the limits. First of all, we put in the upper limit, which is 1. Then we subtract. First of all, let's put in the upper limit. Let's substitute the upper limit here. So we have a to the power 2 over 2. So we have x here. Wherever we see x, we put in 1, the upper limit. So 1 minus. Wherever we see x, there's x here. So 1 giving us sine 4 pi all over 4x. 4 pi. The same as, you can write this term here like this. So then minus, we now put in the lower limit. We subtract that from that. So putting in the lower limit, x here, wherever we see x, we replace it by 0. So 0 minus, this can be written as sine 4 pi x here, which is 0 all over 4 pi. They are all multiplying a squared over 2. So another identity that you need to know is sine 4 pi equals 0. Sine pi equals 0. And then sine 0 equals 0. So those are the things you need to know when you are dealing with problems like this. So now we've solved our normalization constant to be root 2, and our normalized wave function. This was the wave function given to us, which we were supposed to normalize it. So after getting our normalization constant, then the normalized wave function psi bar of x equal the normalization constant multiplied by the original wave function that was given to us to be normalized. Find the normalization constant a of the wave function below and state the normalized wave function. The wave function is given to us as psi of x equal a sine 2x if the interval is from negative pi to positive pi. And the wave function is 0 if elsewhere. In actual sense, the wave function is 0 if elsewhere. It means if we integrate from 0 to negative pi, and from negative pi to positive pi, and from positive pi to 0. If we integrate from here to that, we are going to find a 0. The wave function will be 0 there. It can't describe any probability over there. And here too is going to give us 0. So our main focus is on this limit. The particle must be there if it exists. So that is it to know about this whole problem. Now let's start solving. So in this case, the normalization constant has already been introduced into the wave function. So there's no need for us to introduce a normalization constant again. We just have to take the absolute square of that and integrate with the given limit, negative pi to positive pi. So to normalize this wave function, we need a normalization constant, a value to multiply by the wave function, which is a here. So we are initially going to solve for a, integrating from negative pi to positive pi. So psi of x or squared, the x equal 1. And our psi of x is this term here. So this should be giving us negative pi to positive pi a sine 2x absolute squared the x equal 1. So now let's go ahead and simplify whatever is under the term here. So a to the power 2 gives us, since a is a constant, I'm going to bring it out. So let's try solving it step by step. So a to the power 2 gives us a squared, then sine 2x to the power 2 gives us sine squared 2x, and then the x equal 1. Now a is a constant, I'm going to bring it out. So a squared into bracket, integral from negative pi to positive pi sine squared 2x dx equal 1. So we are going to use the angle reduction formula in trigonometry to evaluate this. Sine squared theta is equal to 1 minus cos 2 theta over 2. So let's try simplifying this. So this sine squared now becomes, let's say, a squared integral from negative pi to positive pi minus 1 minus cos 2 theta. In this case, this is our theta, and we are going to multiply this by 2. So 2 multiplied by 2x gives us 4x, all divided by 2, the x equal 1. Since wave functions are usually in the sign and the form, this trig identity form, it is easier to keep them in memory in order to help your problem solving skills. To improve your problem solving skills. So now the next thing we want to do is to factor half out. This is the same as 1 over, this is the same as half multiplying this to get 1 over 2 here. So we can just factor half out. So a to the power 2 multiplied by half, integral from negative pi to positive pi of 1 minus cos 4x dx equal 1. So this one becomes a squared over 2 integral from negative pi to pi positive pi 1 minus cos 4x dx equal 1. So now let's integrate the term. So a squared over 2. If I'm integrating cos theta, it's going to give me sine theta. But if I'm integrating cos k theta, it's going to give me 1 over k sine k theta. So we are going to apply that idea here. So we have 1, integrating 1, a constant. If I'm integrating 2 with respect to x, it's going to give me 2x. Integrating 5 with respect to x is going to give me 5x. Integrating 1 is going to give me 1x, which is the same as x. So this place becomes x. So minus, integrating this, we have a constant here. So 1 of that constant, 4, we are integrating cos. Then it now becomes sine of everything here. The limit of integration is from negative pi to positive pi, to give us 1. So now we are going to put in our limit of integration, starting with the upper limit, which is positive pi. So a squared over 2. So wherever we see x, we put in pi there. Pi minus sine 4x, which is sine 4 pi. I just divide this whole thing by 4 into bracket. Then minus bracket, we put in our lower limit, which is minus pi. Wherever we see x, we put it minus pi over there. So x, which is minus pi, minus sine 4x, which is sine 4 negative pi. So this will become negative 4 pi. All on 4, close, equal 1. So another identity that you need to know, because solving problems like this usually involve trig, sine or cos, just know the simple identities and you'll be good to go. So we know that anytime you see sine pi, it gives you 0. Sine constant plus pi gives you 0. Sine anything by pi basically gives you 0. So sine 4 pi gives you 0. So we have sine 4 pi here giving us 0. So this term becomes 0. And we have sine 4 pi here. This term becomes 0. So we are going to have a to the power 2 over 2 into bracket. This remains here pi. And what else do we have here? Negative pi giving us positive pi. So positive pi into bracket equal 1. So in this case, pi plus pi gives us 2 pi. So a squared over 2 multiplying 2 pi equal 1. 2 can take care of 2, and then we are left with a squared pi equal 1. Dividing both sides by pi, this cancel that. Then our a squared equal 1 over pi. So taking square root of both sides, our a, which is the normalization constant, going to give us square root of 1 is the same as 1, square root of pi. So this is our normalization constant. So this is what we need to multiply to the wave function that can make the wave function used to predict system. So now we were asked to find the normalization constant, which is a, and this is our normalization constant, and normalize the wave and state the normalized wave function. So the normalized wave function is now stated as psi of x equal a sine 2x, and our a now is 1 over square root of pi. So 1 over square root of pi, then sine 2x. So this is a normalized wave function. If you found this video helpful, kindly subscribe to my channel and give a thumbs up to this video for more educational content like this. You can also refer my channel to your friends. Thank you. Bye.